All right, you guys, so today's speaker will be Dr. Heather Dunn. She is a postdoc here at CCH who received her PhD in quantitative psychology and quantitative research methods from Arizona State University, and her research interest is in measurement invariance. And a fun fact, she participated in a fantasy league for gymnastics during the Olympics and loves cartwheels. And here's Heather.
Thank you, Ellen. And thank you all for coming to my talk. So the title of my talk is A Gentle Introduction to Factor Analysis and Measurement Invariance. And the reason why I chose the topic for this talk is for a very selfish reason. My primary research interest, as Ellen said, is in measurement invariance, so I want my colleagues to understand what I do. So I created this talk assuming that you have no idea what factor analysis is. And by the end of the talk, I don't expect you to be able to conduct a factor analysis because there are a lot of technical details that I'm not going to go over, but hopefully you understand what it is and what it's used for. And in order to understand measurement invariance, you first need to know factor analysis. And feel free to ask questions throughout the talk. So before I talk about factor analysis, I want to talk about probably the most common measurement model, which is the use of scale scores. So many people calculate sum scores to score participants on a particular measure of interest. So I'm working on a project called the ATN, and we administer the Patient Health Questionnaire, which is a series of 9 items that measures the presence and severity of depression, and we calculate the sum score by just literally summing up the item scores. But there are drawbacks to using this type of a measurement model, and one of the big drawbacks is that the items are weighted equally. So this isn't the case with the PHQ-9, but imagine another type of depression inventory where one item is I cried in the last week, and then another item is I attempted suicide in the last week. Those two items shouldn't be given the same weight because they're different indicators of depression. One's more severe. Another example is in education. Imagine a math test where one problem is you have to add 2 numbers together, another is long division, and then another is calculating the integral. So those items shouldn't be given the same weight. Another drawback to using the scale score model is that it's difficult to determine dimensionality. It's not impossible, it's more difficult in comparison to factor analysis. So when you have a set of items, how do you know that you're measuring just depression, for instance? Maybe you're measuring depression and anxiety, or maybe you are measuring depression, but the items are clustering into 2 different clusters, where one cluster is the somatic symptoms of depression, whereas another is the psychological symptoms of depression. So before I talk about the technical details of factor analysis, which factor analysis addresses those drawbacks, I want to talk about the theory behind it. So the theory is that there are certain constructs of interest, such as depression or math ability or personality characteristics like extroversion, that we are interested in, but we can't directly measure them. I can't take a ruler to Scott's head and know his level of depression, for instance. But we can measure the impact of things like depression or math ability, and a common way to do that is by administering items to participants. In the health world, this is typically called patient-reported outcomes. Items are typically common, but you can use other variables like behavioral variables, but items are the most common. And so this relationship between something we can't observe and something we can observe is found not just in psychology and in health, but also in physics and chemistry, where we can't see temperature, but we can see the effects of it on mercury, and it's a causal relationship where the amount of the temperature in the room directly affects the amount of mercury we see in a tube. So this diagram is going to come up again later on in the talk, but I wanted to show it here just so you have a visual representation of what I'm talking about, where I just want to focus on the top half of the diagram. So factor analysis is about having a construct of interest or a latent variable, and this latent variable directly causes item responses. So these squares, y1 through y5, are item responses. and the level of depression you have affects what responses you give. So I've listed 4 different purposes of factor analysis. This isn't necessarily an exhaustive list, but these are the most important purposes. So the first purpose is to condense information. So if we have 25 items, for instance, that we think measure depression, we could run a logistic regression, for instance, on all 25 item scores, but that's pretty cumbersome. Instead, we can summarize all of our information into one factor score and just run one analysis. A second purpose is to determine how many things we are measuring. And by things, I mean common factors or latent variables. So how many constructs of interest are there? Is it just depression? Is it actually depression and anxiety? What's going on? A third purpose is to define the substantive content of those common factors. So for those of you familiar with machine learning, principal components analysis is a procedure in machine learning, and it's very similar to factor analysis, but PCA is atheoretical. It's just a predictive model, and it doesn't care what your items are. So you can put any kind of item or variable into your PCA. They don't have to be related to one another. And then the PCA just repackages the variance, and it tries to condense information in a slightly different way than what factor analysis does. Factor analysis, on the other hand, is a theoretical model where we do believe there are these causal relationships between these latent unobserved variables and our observed variables. And so by defining the substantive content, what does our common factor actually mean? Like, what is it that we are measuring? And finally, the last purpose I have is to identify items that perform poorly. This can be done outside of factor analysis, but from what I remember, if we're using scale scores to determine what items perform poorly, I think most people look at Chromebox Alpha and see how it changes with and without the item, or maybe looking at the variance of the item itself. But with factor analysis, it's a lot more obvious which items are performing poorly. So here is the mathematical model of factor analysis, and for those of you familiar with regression, this really is just a regression equation where we have not just an outcome, but outcomes of interest. So this is a vector of our observed scores. So if we have 8 indicators, this is an 8x1 vector of continuous observed scores. And that's equal to a vector of intercepts plus a matrix of loadings, which are analogous to regression coefficients, times our predictor scores, in this case our common factor scores, plus a vector of what are called unique factor scores, but these are just residuals. In factor analysis, we assume that these unique factor scores, each item has a unique factor, and each unique factor has a variance, but none of the unique factors covary with any of the other unique factors. So the variance covariance matrix of our unique factors is equal to theta, where theta is a diagonal matrix. And that'll be important later. So this equation, very similar to regression, except our predictor is unobserved. We don't have scores, so we can't just use a regression analysis for this. So in combination with that equation, we also make some assumptions in factor analysis. The first assumption is that the common factors are uncorrelated with the unique factors, and this is important because it allows us to decompose the variance of every single observed variable into variance that is due to the common factor and variance that's due to a unique factor. The second assumption is that the unique factors are mutually uncorrelated. That's why the theta matrix is diagonal. And the third assumption is that there is a linear relationship between the factors and the observed variables. We can relax that assumption and allow for quadratic relationships, or our outcome can be binary if we want, etc. But when taking that initial equation and these assumptions together, we get the following expectations. I'm not going to go into too much detail about these equations, but this first equation is about the expectation of the covariance structure, and the second is about the mean structure. And the important point to point out is this first equation. So what this is saying is that our model implied variance covariance matrix of our observed variables is equal to a proportion of variance due to just the common factor and a proportion of variance due to the unique factors. So the common factor and unique factor are split up. So returning to this diagram, these y squares, these are our observed variables, so our 5 items. And we see that every single item has 2 different causes. There are 2 arrows going into each square. And this latent variable is called a common factor because it's what these items have in common with one another. And then each item has a unique variance because this is what is unique to that item. And once we account for the common factor, the unique factor is just what is left over of the item. And together, the common factor and the unique factor account for the entire variance of the observed variable. Any questions so far on that? Okay. So there are 2 different types of factor analysis: exploratory factor analysis and confirmatory factor analysis. And with exploratory factor analysis, you definitely need to do this when you're developing a scale and to make sure that you're measuring what you think you're measuring. And so you have a set of items and you're not sure how many factors there are or which items go with which factor. And so EFA will tell you that. So you run multiple models to test the fit and the interpretability of your models. Confirmatory factor analysis, on the other hand, you have strong theory. You know how many factors there are and you know which variables go with which factors. So in doing CFA, you should theoretically only run one model, but in practice, a lot of people run a CFA and then like to do exploratory work on their CFA to improve the fit, which is not necessarily a no-no, but people aren't necessarily honest with all the modifications they make with their CFA models. So for the rest of the talk, I'm going to be talking about CFA because measurement invariance is a type of CFA. So now I'm going to transition to measurement invariance. So let's assume I wanted to measure the height of everybody in this room, and I created pairs of people where each pair consisted of a man and a woman who had the exact same height. So one pair was a man and woman that were 5'8", another pair was a man and woman who were 6 feet tall. It'd be really concerning if I then measured their height and found for every single man, I overestimated their height by 1 inch, and then for every single woman, I underestimated their height by 1 inch. Why am I having this systematic difference in how I am measuring people? So that's what measurement invariance explores. Is there a systematic difference in how we are measuring different groups of people on these constructs of interest? So when we use a common factor model, the factor structure should be the same across groups. The latent variable should have the same relationship to the items across groups of people. And if the relationship is different, can we make conclusions validly? So here's the mathematical representation of measurement invariance. So this is saying that for the probability of obtaining a particular set of observed scores given your latent variable score and your group membership is equal to the probability of obtaining a specific set of observed scores given just your common factor score. In other words, knowing what group you come from does not change your probability, which intuitively makes sense. If 2 people have the same common factor score, you would expect them to have the same probability of getting a particular observed score. But when we have a measure that's not invariant, the probabilities differ by group. So for instance, assume all 3rd graders in the state of California are administered a verbal exam. If a boy and girl with the same verbal ability have different probabilities of obtaining the same observed score, then the exam is not invariant by gender. So there are important aspects of that sentence to point out, with the same verbal ability. So its mean differences are allowed. So it's definitely possible that maybe girls have a higher verbal ability than boys. That's definitely acceptable. It's when we match a boy and a girl on the same verbal ability, if they have different probabilities of obtaining a particular score, that's when it becomes an issue. And it's important to say probability because of random error. We don't necessarily expect two people with the same verbal ability to get the exact same score because there's measurement error involved. So one example of this comes from a verbal exam, where it's one of those analogy questions that we all had to take on the SAT or the GRE, where we have decoy is to duck, as A, net is to butterfly, B, web is to spider, C, lure is to fish, and D, lasso is to rope. So before I learned about this question, I had no idea what a decoy was in the context of a duck. Like, no clue. And when we match boys and girls on verbal ability, we find that boys tend to answer this question correctly more often than girls do, because knowledge of hunting and fishing jargon helps answer this question. So it's something outside of your verbal ability is helping you answer this question and causing that group difference. And the correct answer is lure is to fish, because just for those of you who don't know, because I definitely did it, a decoy is like a wooden duck, and when you put a wooden duck out there, ducks flock to it. So in the same way, fish flock to a lure. So I didn't know that beforehand. So to give a visual representation of what non-invariance looks like and what a group difference in the construct looks like and what is what, I have two different pictures. So this first picture, we have a predictor variable, which in our case is our common factor variable, so depression, for instance. And on the y-axis, we have our criterion. In this case, think of an item. And right now, I've been showing models that assume your outcomes are continuous, but it's easier to talk about items. So just pretend your item is a continuous variable. We have this line here, which is a regression line and reflects the strength of the relationship between the latent variable and our item. And so this is our expected score on the item given our latent variable. And we have two groups that are measured, group R and group F. Group R stands for reference group and group F stands for focal group, but that's more in the education literature. So we see that there are mean differences where the mean of group F is roughly 3 and the mean of group R is roughly like 5.25 on the latent variable, and that explains why we see observed differences on our items. But this item is invariant because when we look at a value of 4 on our predictor, for instance, somebody in group F and somebody in group R are expected to get the exact same score. So this item is invariant. This item, however, is not invariant because we have two different predicted scores depending on what group you're in. So when we look at a value of 4 on our latent variable, for group F, we expect an item score of 2.5, but then for somebody in group R, we expect an item value of 5. So does that make sense to everybody? Okay. So another example of non-invariance that comes up pretty commonly, it's a replicable effect, is when you look at a depression inventory and it contains the item I cry easily. Because men and women are socialized differently in terms of expressing their emotions, when you look at a man and a woman with the same level of depression, women are more likely to endorse that item than men are, even though they have the same level of depression. So that indicates that it takes a higher level of depression for men to cry. So what do we do with this item? If there's a different relationship across group, what's the valid thing to do? We could drop it, but then maybe we're missing an important part of our construct. We could just ignore the fact that we found this difference and model it to be the same, or we could model the difference. And people vary on what the correct solution is, but the last solution is the one I usually work with, which is you just model the non-invariance and things work out. So to get into the technical details of measurement invariance, we're using the same factor analysis model that I showed before, but now everything has the subscript of G. Okay, so the first model we test is the configural invariance model. And here we constrain this loading matrix to have the same dimensions across groups. So we're measuring the same constructs of interest, and the same variables define those constructs across group. So the configuration of our loading matrix is the same by group. And the way we test if this model fits is by looking at global fit indices and local fit indices. So hopefully this model fits well. If it doesn't, it could be because your groups are measuring different things, or it could be that the model itself just doesn't fit well in either group. An example that I find kind of interesting is sometimes finding non-invariance is a good thing, and it's an interesting finding, where I don't know if this is a real example, but it's one that my professor told that just stuck with me because I think it's really cool, where they measured employers and they administered a set of items that measured leadership ability. And so before the intervention, they conducted a factor analysis, and one factor came out. There was one factor of leadership ability. But then these employers were put through an intervention where they went through leadership training. And then after that intervention, they were given the exact same items, and the researchers ran a factor analysis again, and then they found 3 factors came out, because the employers realized that being a leader, it's not just one thing. There's actually multiple dimensions to being a good leader, and you can succeed or fail at any of these dimensions. So we can't compare the scores on those variables across time, but the finding of non-invariance in and of itself is interesting. So once we test the configural invariance model, we can then move on to testing the metric invariance model. And here, our loading matrix is constrained to be equal across group. And this invariance model is nested within the configural invariance model. And so we can use a chi-squared difference test to test the difference in fit of these two models. If the chi-squared difference test is not significant, then the fit is relatively the same in the two models. And so we retain the model that is the most parsimonious. In this case, the metric invariance model, because we're measuring, or we're estimating fewer loadings compared to the configural invariance model. If the chi-squared difference test is significant, then that's saying that the fit has significantly decreased, and this metric invariance model does not fit as well as the configural invariance model. In other words, the loadings are different across groups. So assuming that our metric invariance model fits well and our chi-square difference test was not significant, we move on to testing the scalar invariance model. And here we constrain the intercepts to be equal by group. And once again, we conduct a chi-square difference test between this model and the metric invariance model. If it's not significant, then we choose the more parsimonious model, which is the scalar invariance model. And we can move on to testing the strict invariance model. And here, our unique factor variances are fixed to be equal by group. And we do the same procedure and analyze a chi-square difference test. So, for those of you who are algebraically minded, that probably made sense. But for those of you who are more geometrically minded, I have some pictures to more clearly illustrate what's going on. So once again, we have our common factor on our x-axis, and then our observed variable, our item score, on our y-axis. So when our loading and our intercept and our unique variance differ by group, this is what we see, where we have two different groups, a blue group and a gray group. And so you notice that the loadings are different because the slopes of the lines are different. Also, assuming this is the 0 point, the intercepts are different. And then notice also the spread of the dots around the group line. The gray group has a much wider spread compared to the blue group, where the dots are much more tightly packed together. With metric invariance, we have our loadings be equal by group, but the intercepts and the unique variances are different. So the term weak is here because people sometimes use the terms configural, weak, strong, and scalar, but I prefer the terms configural, metric, scalar, and strict because there's connotations with weak and strong that I think a lot of people stop their measurement invariance testing with the strong invariance model, but they really should continue on and test to the strict invariance model. So scalar invariance or strong invariance is when both the loading and the intercept are equal by group. So the expected score is the same for each group, but the probability is still different because the unique variances are different by group. So that's why we should continue testing and hopefully have strict invariance. Any questions on the levels of invariance? Yes.
It's partly a heads up. I'm sorry I'm going to have to leave and give a final exam because it's a great overview. I did have a question about this. Does it matter how the factor models are being fit to get the right tests, or is it being done with maximum likelihood factor analysis? Is that?
Yeah, there's different estimators you can use. I think maximum likelihood is the most common though.
Because that would then support the likelihood ratio test to be the
right.
to be the chi-square. So those are all understandable as likelihood ratio tests.
Yes, exactly. Yeah, because you could do like unweighted least squares, weighted least squares, etc. So there are different options, but I think maximum likelihood is the most common.
Sorry.
Thank you for coming. So at any stage of this testing process, our chi-square difference test could be significant, indicating that one or more of our parameters differ by group. But which parameters? And so there's a whole literature on how to figure out which parameters are actually causing that misfit, but that's a whole other talk. But let's say we do find that we have an item that is not invariant, so what do we do? And I kind of went over this earlier in the talk, but there's debate about what to do because, like with anything, it depends. So if we have a 20-item scale and one item is non-invariant, to me, that's fine. And it's still valid to compare group differences on the construct of interest. But if we have a 20-item scale and 10 of our items differ by group, well, what does our common factor actually mean? Like, why are we seeing all those differences? And so there isn't a clear cutoff about what is like how much is acceptable versus not. Statistically speaking, we only need one item to be invariant and all the rest can be non-invariant, but I don't think anyone would feel comfortable making comparisons based off of that. So it's not really a statistical question, it's not a question that statistics can answer. It's more of an issue of validity and how much proof you need to compare the scores. And just a fun fact, for my dissertation, I created 4 different effect size measures of partial invariance to try to help us determine how much non-invariance there is. And my overall goal in life is to create a range of values for those effect sizes and call it the gun range based on my last name.
Oh, okay.
So this talk, all the models that I presented in this talk were for continuous outcomes, but then I kept saying items just because that makes more sense, I think. And so there is a thing called categorical confirmatory factor analysis, and it is the same idea, but when you have binary outcomes, things slightly change. And there's also item response theory, which these two models, I guess you could call them, they are identical or they're equivalent to one another. The difference between them is where the marginalization happens, if it happens in the latent variable space or if it happens across items, but they are the same thing. Yeah, so the item response theory is more common in educational testing, so ETS. Like all of your GRE scores and SAT scores were scored and created by an item response theory model. And plus there's better software for IRT versus categorical confirmatory factor analysis, so I think a lot of people lean more towards item response theory models. So that's all I have for you today. Are there any final questions about anything I talked about? Yes.
So thank you. Good presentation. So you mentioned the education, and I could see this being used a lot there, but also thinking of possible applications with our adolescent trials network data, for example. Looking at the way we measure things in our HIV negative sample versus, with our positive youth. And, looking at measurement and variance there and some of the scales. Since you've been here a little while now, I guess you've probably started to think of applications for this to our data, and I'd love to get your thoughts on that.
Yeah, the only two that kind of popped into my head are the PHQ-9 and is it G87? Because I don't know, unless I'm missing something, I don't know of another kind of construct where there are multiple items that measure the same thing. Where I think there are a lot of questions that are like individual items, and there I think are
maybe more in the Africa data there might be that situation. And
that's what Ellen
you have
told
possible
me,
subgroups there with HIV positive women, HIV negative.
Right, and more potential factors there. Whereas kind of other than PHQ-9 G87, I didn't really see anything else.
Yeah, you're right. Actually,
combine.
We might not have a lot of scales.
So there's a lot of discussion around eliminating standardized tests, like the SAT. Has there been a lot of research on this done? Because saying that low income and African American primarily it's biased against them. So would it be possible, or is it not even possible to correct for scores that are biased against low income groups, or is it more of just they're disadvantaged? It's not like a question of like they might know more about something that's topical.
Yeah, it kind of depends on how you want to define your construct. Because that question I showed with the like hunting and fishing, maybe the person who created that test wants that to still be an item because it is important to the construct that they're specifically looking at. Like it's not just kind of general verbal ability, but it's like a specific type of verbal ability that they're interested in or something. In terms of because like the question, it's harder to get at your question because you're essentially, if I understand correctly, you essentially ideally would like it if there were no mean differences across groups of people, whereas measurement invariance is about looking to check to make sure that the probabilities aren't different across people given a particular score they have, but it still allows for mean differences. And so if we have like women scoring a lot less than men, it still can be an invariant measure, so it doesn't really get at that.
So just a general comment about using scales, and some of us we've done work in global settings, so we have a lot of scales that have been developed and standardized in the US, and the examples that you gave are looking at potential differences between men and women. I was wondering if you can comment on some of these cultural aspects, so where scales are translated in a different language and then how different communities from different countries interpret the construct.
Yeah, no, that's a very common application of invariance testing for sure, to make sure that the translation is occurring appropriately, essentially. And so an example that my professor would talk about was in German, when you try to translate the question from a depression questionnaire, like I feel blue, apparently blue in German means drunk, is what he said. So a very different meaning for German participants. I think there's like an example with Spanish where like using the term alto and how if you use that in an analogy question, Spanish speakers and English language speakers interpret that differently because alto has a different meaning. So it's definitely an important application when looking at cross-cultural studies, and when developing measures, I think most people check for invariance when they're translating.
I take it that your presentation was crystal clear.
I answered everyone's question.
All right. Sounds good. Well, thank you.
Thank you.
Thank you.